You're listening to What Do Scientists Do? It's a show where I talk to a different guest each episode and they teach us all about their favorite science topics. My name is Jessica, and today I'm joined by Ian, a particle physicist, who teaches us all about everything from the teeniest, tiniest things in the universe to some of the biggest things. Hello, everybody. Welcome to What Do Scientists Do? My name is Jessica, and today I'm joined by a very special guest. Could you give us your name and your pronouns, please?
Yes, my name is Ian. My pronouns are he, him.
Nice to meet you, Ian. And what kind of scientist are you?
I am a particle physicist.
What is that?
So, a physicist in general is someone who tries to describe nature using math. So, it's a really broad field. It can be, on very big scales. There are astrophysicists who look at, planets and stars and figure out how they move and why they form. There are sort of everyday physicists who look at, why does it feel like you're being pushed to the side when your car turns, or why does a figure skater go faster when she pulls her arms in. But I am a particle physicist, which is the smallest scale. So if you zoom in to teeny tiny scales far beyond what you can see, so even smaller than anything you can see with a microscope, you see that the universe is built of these things we call particles. They're like little building blocks that we use to make up everything else that we see. And I study all the particles that we know about and looking for some that we think should exist, but we don't know exist for sure. And I study how they interact with each other.
That's super cool. So you mentioned that lots of these are too small to be seen with a microscope. If we can't look at them with really powerful microscopes, then how do we know they're there?
So there's a couple of different ways we can see their effects. So if we have a particle bump into something that we can see, it might, produce a little bit of light, or it might move something. It'll create a little bit of energy. So we can see their effects sort of after the fact. And what I do is I'm a high energy experimental particle physicist. So we build these really, really big experiments where we accelerate little particles to, the fastest speeds we can on Earth, and we smash them together. And then what that does is it makes a big mess, and we see that mess as energy in what we call detectors. And these detectors are just fancy pieces of technology which are used to measure energy in various ways. And we see, it makes this big spray of energy when we collide these particles, and we can see, certain particles behave certain ways, and that's how we can figure out what particles we made and what particles we started with, and et cetera, et cetera.
So this might have a really complicated answer. I'm not sure. I don't know much about particle physics. How do you get them going that fast?
So it's a combination of things. So we start with hydrogen, which is the smallest atom. So atoms are sort of the building blocks of people and matter, and everything you see around you is all made of atoms. Atoms are actually made up of smaller particles, but we can talk about that in a bit. But basically, we take hydrogen, which is a gas, and we take off its electrons. So normally hydrogen is made up of a proton, which is a bigger particle, and then a little electron that goes whizzing around it. We take off the electrons, and that means the hydrogen is now charged. And then there's an interesting quirk of charged particles where if you put them in a magnetic field, so if you take a big strong magnet and you put it next to a charged particle, it'll bend. So if it's moving straight, it'll start to turn. And so what we do is we take a stream of this hydrogen, which is charged, and we put it in these huge magnets, the strongest magnets that are on Earth right now. And it starts to bend them and push them forward. And we basically send them around a big ring over and over again until they pick up more and more speed. And eventually, at some point, they're going, a fraction or a very large fraction of the speed of light. And the speed of light is sort of the fastest thing in the universe, the fastest known speed. Nothing can go faster than it. So these particles are going very, very close to that speed. And it's basically just magnets in a ring, and we circle them over and over again.
Wow, that's very cool. What is that whole thing called?
So the whole apparatus is called a particle accelerator. I work with ATLAS, which is one of the experiments on the Large Hadron Collider. So the LHC, Large Hadron Collider, is the world's largest particle accelerator. It's based in Switzerland, and it's actually so big that it has to sit on the border of Switzerland and France. So it's too big to be all within one country because of where it is. So it's this huge ring, which we use to accelerate these particles. And then it has 4 main experiments on it. And I work for one of them, which is called ATLAS. It's the largest experiment there. It's actually the world's largest scientific experiment on Earth. So we get, it's this fun contrast where I work for, the world's biggest experiment to study the world's smallest stuff. But you just need these ginormous pieces of equipment to get the particles up to that amount of energy, and then also be able to see the mess you make. So the ring itself is actually 2 rings, because we send one particle in one direction and one particle in the opposite direction, so that when they meet in the middle, they are going at each other instead of in the same direction, and they can collide and just spray us with a mess.
That's really cool. How big is it? Do you know?
It's a 27-kilometer ring. So the ring around is 27 kilometers. And then my experiment that I work for it's like a big cylinder. So it's like a big can. And the diameter of the circle part of the can is 25 meters. So it's like 25 meters tall. And then it's about 40 meters wide. So very, very big.
Yeah, so even just like if this was a water slide for particles, which is how I'm imagining it, the water slide, when you go into it, would be 25 meters tall. So that's like a quarter of a soccer field by like 40 meters, which is like almost half the soccer field. So even just the tube part is massive.
The tube itself is a lot smaller.
Okay.
I mean, it's still very big for accelerating these particles. The ring itself is probably a meter wide. I haven't actually seen it in person yet. I'm hoping to soon, but it's about a meter tall, the ring. So the tube is a meter tall, even though the particles are teeny tiny. But then when we collide them together, there's like 4 places where we actually smash them together. And those are the 4 experiments. And the one I work for is at one of the places where we collide them. And that's what's 25 meters tall and 40 meters wide.
It's still really cool, though.
Mm-hmm.
That's a massive, massive experiment. That must have taken a lot of like cooperation to put together something that huge that crosses like the borders of multiple countries too. Do you know how many people have worked on it overall?
Overall, no. I know that my experiment employs over 3,000 scientists, and that includes many, many physicists, but also people from different disciplines. So we have, engineers who help build things, and we have technologists and all sorts of other stuff. So working for Atlas, there's about 3,000 scientists, and they're from many, many countries. So I think there's over 100 different countries which contribute various people and parts to the experiment. And then that's only one of the experiments. There's 4 of them, and they all work together on the Large Hadron Collider, which is part of CERN. So CERN is sort of the house of the experiment and the accelerator, and it's this huge international collaboration. So people from all over the place, Russia, China, Chile, the United States, Canada, just as an example, they all come together and work on a common goal. And it's actually it's a really nice, collaborative international effort to get this thing going, because no one country could do it by themselves.
Yeah, that's some really cool teamwork going on. What is your specific role in all of this?
So my role is currently changing. I just started my PhD, so I'm going to be moving on to some new research. But when I was working on my master's, we were using the data we collect to look for dark matter. So dark matter is this sort of big mystery in the universe. It's not as scary as the name might sound. Dark matter is matter that when we look out in the universe, we see that there should be more stuff than what we can see from stars and galaxies and things like that. There should be more stuff because the way, gravity is the force that keeps us on the Earth, and it keeps the Earth going around the sun. And so we're very confident in our ability to measure things using gravity. And so we see that if we measure things with gravity, it looks like there's a lot more stuff than if we just measure things using light. So if we look out into the sky and we look at a galaxy, for instance, we see a lot of light coming from it from all the stars. But then when we try and measure, properties of this galaxy using gravity, it looks like there's more than just what we can see. So there's some matter in the universe that doesn't interact with light, we say. So that means it doesn't reflect light and it doesn't produce light. So it's not, a star or something like that. And so we call it dark. And so dark matter is this big mystery because we're pretty sure it's there. We can see its effect. We know it's interacting gravitationally, but we have no clue what it is right now. So there's been a lot of work to try and constrain what it means. So to constrain is like to reduce the possibilities of what dark matter could be. So that could be, how fast can it be moving and how heavy can it be? And there's been a lot of work to try and figure out, sort of reduce the range of those options, but we still don't really know what it is. And so for my master's, what we were doing is we were looking at particle collisions that may have produced dark matter. So if you take two regular particles, you smash them together, you might produce dark matter. And then because of the way it works, you don't see dark matter in your detectors, but if it decays into other things, so this is where things get a little complicated. So detectors are very useful for looking at charged particles because of what I explained when charged particles and magnetic fields are next to each other. There's the effect of the charged particles curving and various things like that. So if the dark matter, which can't have a charge, and that's because anything with a charge will interact with light. So if the dark matter we produce decays into something that does have a charge, we might be able to see the decay in our detectors. So we're looking for a collision that produces something we initially can't see and then produces something that we can see. And sort of that, the missing component there is what we're trying to figure out. Is that dark matter or is it something else that we just don't know? And so for my master's, we were looking at a version of dark matter that would have a very particular decay so that it would be very easy to find in our data. And that's sort of important because the way most particle physics experiments work is that you collect a lot of data and then you analyze it with a goal in mind. So a normal science experiment is you come up with your hypothesis, I think this, and then you go out and you take measurements that would support that, and then you look at your data and say, is my hypothesis right? But a particle physics experiment is really expensive. So you can't make a new one every time you have a new hypothesis. So what you do is you make something that's very general. You collect a lot of data, and then you go at it with different hypotheses and see, does the data support this hypothesis? Does it support this hypothesis? And so that's the way my field works, at least, which is a little bit backwards. And so we are going in with this hypothesis of some version of dark matter, and we're looking to see whether it's there. And we actually haven't finished the analysis, so we don't know yet. We could find it, we might not. It would be very exciting if we did. But yeah, so that's what I was working on.
That's very cool. Do you know how long it would take you to know if you found it?
Yeah, I guess the problem there is even if we think we found it, it's really hard to claim that you've actually discovered it. And part of that is, like I said at the beginning, these things are too small to be seen. So you can't actually, go with a microscope and say, oh yeah, there it is. We found a dark matter particle. We know what it looks like now. So what we would say is if we found some sort of evidence for it, that means there's evidence to support our theory. We would try and refine our theory, make it more strict, and say like, what are the parameters of our theory? So what are the options? How heavy can the dark matter be? And what are the ways it can interact with other matter? And you try and reduce those possibilities, and you look at the data again and again and again until you get more and more evidence that supports your theory. And then eventually, when you have a lot of evidence and very little uncertainty, so uncertainty comes in a couple different ways, but usually it's basically it's how sure are you of your measurement. So if you reduce your uncertainty and you collected a lot of evidence, then you can say, okay, maybe we found dark matter. But if we found it initially in the work I was doing, we wouldn't go out and claim that right away. We would say, okay, we found some sort of evidence. Let's keep looking in this direction. And if we don't find it, that's not the end of the world either. It just means that, okay, maybe this isn't the way to look, and we'll look for something else.
Do you think that we're going to figure out what dark matter is in the next 20 years, 50 years, 100 years?
I think we're definitely getting closer. There are, tons of scientific efforts to try and figure this out. And it's not just my experiment. There are many, many, many experiments all over the world trying to figure out this question. So it's very likely, I would say, within the next 100 years for sure is my guess, which is a sort of as safe as bet as I can make. I would assume it's probably less than that, but you never know. In science, sometimes these mysteries just take forever to figure out. It's already been, more than 90 years since we first discovered the initial evidence that led us to believe that dark matter exists. So it's been a long time, but hopefully, as more and more people work on it, it will get closer to figuring it out.
Why is it important to figure out this kind of stuff?
That is a very good question. So at the end of the day, if my work discovers dark matter, it really has no impact on you or me in our everyday life. But it is one of sort of the big questions of our universe. This dark matter, we think there's a lot more of it than our regular matter. So it's actually a huge fraction of the universe that we just don't know what it is. And answering the question of what is it is, it's important in a sort of philosophical sense. So it's a good question to ask, and it's a good answer to have. But day to day, it's not going to change anything. But on the way to discovery, particle physics is usually something that produces a lot of offshoot benefits. So what that means is, as we build more experiments and we refine our techniques to search for things, we develop a lot of technology and a lot of skills that are really useful in other places. So I'll give an example. CERN, like I said, is the home of my experiment, and it has been producing these particle accelerators for many years. And one of the offshoot benefits was a version of a cancer therapy. So they use basically a mini particle accelerator that you shoot at cancer patients, and it helps get rid of tumors. And it's something that would never have come along if we hadn't just been looking for particles out in the universe. So it's really hard to say what the benefits are going to be in the future, but it's almost guaranteed that there will be some benefit to us in our society from looking. And then having the answer in the end may also prove really useful to other theories and may eventually actually be useful to us if we can, maybe we can figure out a way to harness dark matter for energy and it'll solve the energy crisis or something like that. It's impossible to say right now, but I think it's still important to look.
Yeah, I think a lot of the far-off predictions sound like sci-fi. It's so hard to know
Absolutely.
what you could do with that information. Like time travel, I don't know, but it's still very, very cool and seems to have lots of benefits in the process. Oh yes, is there one thing that you think everyone should know about particle physics?
I think what I would want everyone to know is that there's still a lot that we don't know. So some of the biggest unanswered questions about our universe are still unanswered, and it's a matter of time until they hopefully get answered. But along the way, we're going to need people who are curious and interested and eager to dive into these really, really big questions. And I think it's easy to look at something like particle physics, which has made tremendous progress in the past couple decades, and think, okay, we're all done there. We know all the particles. Let's move on. But there's actually these huge unanswered questions that we still need people to try and address. And I think it's a fun and exciting field if you can get into it. And we're always looking for new people.
Super cool. So it definitely sounds like the kind of field for people who want to know all the details. Like you just keep looking, closer and closer and closer until you end up as a particle physicist who wants to know the exact details of what's going on, which then gets you back to the scale of the universe somehow at the same time, which is very cool. It's like you're doing the smallest things and the biggest things all at once in a way. Super cool. Well, thank you so much for joining me today, Ian. This was really fun and very cool.
Yeah, my pleasure. Thank you for having me. It was a great time.
And as always, a big thank you to everybody listening. For more science fun, past episodes, and other information, you can visit bit.ly/whatdoscientists-do, or you can follow us at ScientistsDoPod on Twitter or Instagram. Do you have a question that you'd like answered by a scientist? Send us an email or a voice recording at whatdoscientists-do@superstaff.ca or message us on social media. Thank you so much for listening, and I'll see you next episode. Bye for now. This show is made by Supernova at Dalhousie University, a network member of Actua. For more information on our summer camps, workshops, and more, visit supernova.dal.ca.